Okay, guys. Lesson 12.4 is probability distributions. Okay, so we're going to talk a very brief little. You're going to see brief couple little tree diagrams today, but for the most part, again, it's all based on our basic. What we've done is theoretical probability, just the theory of probability that you roll a die, it's a normal die, all 6 sides are equal. So that's our theoretical probability, and that's what we're working on. Now, in this discussion to get us started, Mr. and Mrs. Mason have 3 children. Assuming the probability of having a baby girl is 5/10 and the probability of having a baby boy is also 5/10, there's 2 provided models here. Okay? And as you look, they're kind of, they're looking at the total options of having girls. There's model A, where you have these options for probability. And there's model B, where you have those options. So the first part of this discussion, which model represents the situation correctly? Model A or model B?
I don't know. I want to say model B.
Why do you want to say model B?
Because it's bigger.
Because it's bigger. Well, not exactly the explanation I need here.
Well,
A is just wrong, doesn't really do it for me either.
Model A is just stronger gut feel.
Gut feel.
Yeah. No.
I'm getting that's the idea of everybody.
Well,
It's
so
just,
is model B.
Model B is all girls go landed.
Oh, wait, is it?
and
Yeah.
well, and what they're doing is they're just showing you,
Well,
like in this case,
so what's the
here's 3 girls. Here's having this combination would have 2 girls. This combination would have 2 girls. This combination would have 1 girl. So on and so
It
forth.
shows more combinations.
Okay.
Spread smaller.
And here's the thing to think about probability-wise. This is showing that the probability of having all 3 kids being girls is 0.25. Probability of 2 of the kids being girls is 0.25. Probability of 1 of them being a girl is 0.25. And the probability of none of them being a girl is 0.25.
That's right.
Is it going to be equal probability every time?
Yes.
No.
It's not.
It is in the other one.
Okay, so think about this.
They both wrong.
What's the probability that the first child is going to be a girl?
0.5.
0.5. What's the probability the second child is going to be a girl?
0.5.
0.5. Does whatever the first child was, whether it's a boy or a girl, does that affect what the second child is?
No.
No. What's probably the third child will be a girl? 0.5. So, is it going to be the same all the way across?
Yeah.
Yeah. Wait. What do you
Well, okay, I asked that in a bad way. My apologies there. Okay. In terms of, here. Okay. 5/10 chance a boy, 5 chance it's a girl. If it was a girl, now what about the second kid? Second kid could be a boy or a girl. If the first kid was a girl and the second kid was a girl, what's the chance of there being a girl again or a boy again? Well, it's half and half again, yes? Now, so there's one option of having 3 girls. As you look at all the options, do we have the same amount of 3 girls, 2 girls, 1 girl, and 0 girl here?
No.
And the answer is no, okay? There's only one chance of getting 3 girls. How many chances of getting 2 girls are there? I say it looks like 3 there. So 3 chances of getting 2 girls. How many chances of getting 1 girl? 3 also. How many chances of getting no girls? And that's just 1, because that would be the boy, boy, boy option. Okay? And so the idea, which one represents the situation correctly, we are looking at model B. Part of that is because they are independent events. Okay? The birth of one child does not affect what the next child is going to be. So I'm going to say model B. And I think my big thing is that each event is independent here. Question B, what's the probability that Mr. and Mrs. Mason have 3 girls?
12.5%.
Okay. How many 3-girl options are there? 1. Out of how many combinations are there?
1, 2, 3, 4, 5, 6, 8.
So that is
1, 8.
1 out of 8, yes? And we've been there, done this. 1/8 could also be written as what else?
0.125.
0.125 or
12.5%.
change that to a percent, 12.5%. Okay. And then C. Compare the probability that the Masons' first child was a boy and they then had 2 girls to probability that their first 2 children were girls and then they had a boy. Does the order affect the probability?
No.
So what's the first one through? First child was a boy, and then they had 2 girls. How many times does that happen if we start looking up here? So boy, girl, girl. So first one being a boy, yes?
Yeah.
Then what?
Girl.
Girl, and then
Girl.
girl. How many times did that happen? How many paths could I follow there and get that option? Just, well, it's just one path. So 1/8. Compared to, what's the other one?
1/8.
2 girls, oh wait, no. First 2 children were girls, and then they had a boy. So this would be girl, girl, boy. Well, have you tried?
1/8.
Girl,
Doesn't work.
and then if they have a girl, and then they have a
2 boys.
boy. So that's how many options? That's just one path out of 8 paths. Okay? So, basically we're looking at 2 girls and 1 boy. What's probably that they have 2 girls and 1 boy? It's 1/8. Does the order make that difference? No, the order is not going to make that difference, okay? So order does not make a difference. And again, this comes back to because they are independent events. Okay? Independent events. And if you think about it, each time it was 1/2 times 1/2 times 1/2, which is always going to be 1/8. Okay. So a little bit more practice with the tree diagram there, getting us back into the probability. You have a little bit of vocabulary there next on your paper. I think I've used probably the expression sample space, I think. Okay. With that in mind, a sample space is a set of all possible outcomes of a situation or experiment. For example, if I go back to what we just were, okay, BGG, that's part of the sample space. GGB, that's part of the sample space. Each of those options is one of the pieces of the sample space. Now, our big topic today is probability distribution, and probability distribution for an experiment is a function that assigns a probability to each outcome of a sample space for the experiment. Okay? Basically, they're going to be giving sample spaces with, I call these braces. It's like the squiggly parentheses. Okay? And they're going to want to know the probability for each value in the sample space. And I'll explain what that means in each case. So as we look at A, we look at trying to set up the probability distribution, so assigning the probabilities. Tio and Henry are running for president of the student council. You will select a campaign button at random from the box containing 3 Tio buttons and 3 Henry buttons. You'll record the number of Tio buttons that you get. What is the theoretical probability distribution for the sample space 0, 1? Okay, now, understanding 0 and 1. That 0, 1 represents, what are we trying to do the probability for? The number of Tio buttons you get, yes? So you are just picking into a box and picking out one random button. What are your options?
50%.
Okay, 50%. But the idea that either yes, you could get a TO button, yes, or no, you don't get a TO button because you would pick a Henry button. So this 0, 1 here, the sample space 0, 1 represents how many TO buttons you can select in one trial. You can either get 0 TO buttons or you can get 1 TO button. So thus, the possible outcomes are 0 or 1, and that's what they're asking you. And so when I go to find the probability of 0, that's going to be the idea of what is my probability of not picking a TO button. So when they ask you for probability of 0 in this sample space, 0 represents essentially a failure. You did not pick up a TO button. And what is my probability of not getting a TO button?
0. Or wait, 50%.
50%, because there are how many non-TO buttons?
3.
3 out of how many total buttons?
6.
6. So 3 out of 6, which is 1/2, 0.5, 50%, whatever variation you want to give there, yes? So the other option then is the probability of 1. And so that probability of 1 is going to be the probability of picking a TO button on that one draw. So what's my probability of picking a TO button?
50%.
Okay, same thing, right? This time there are 3 TO buttons out of 6, which is 3 out of 6, 1/2. And so when they ask what is the probability distribution, well, probability of 0 buttons is 1/2. The probability of 1 button is 1/2. So when they're asking you for that probability distribution, they're asking you for finding the probability of each item. Okay. Now, what changes on B? Now you plan to select a button at random, put it back in the box, and then select another button at random. You'll record the total number of times that you get a TO button in the experiment. Define the theoretical probability distribution for the sample space. This time our sample space is 0, 1, 2. And how does this probability distribution differ from distribution in part A? So when we get done here, the idea I want is, okay, what is the probability of 0, probability of 1, or the probability of 2? That's going to be our probability distribution. Now, we added a 2 in this time because this time it's not just one draw, but it is 2 draws, yes? And we can think of this in a couple different ways. I don't know if you're going to like this, but I thought of it as a tree diagram. Or basically, I'm going to say tree diagram, but basically listing all my options. When you draw that first button, what could you get? You could get a TO button, or you could get a non-TO button. I'm going to say a Henry button since that's my only other option, but I agree, TO or non-TO. Then what did you do? You put that back in the box, and then you selected another button, yes? If my first button was a TO button, what are my options this time? You could get a TO button or a Henry button. If I got Henry the first time, what are my options the second time? Also, TO or Henry again, yes? Now, maybe I should have done this earlier, but if we look at all these, we look at the options, the combinations. You could have gotten TO the first time and TO the second time. You could have gotten TO the first time and Henry button the second time. If I got Henry the first time, I could have gotten TO the second time or I could have gotten Henry Buttons both times. Okay, that's my sample space. Those are my different options. I could get T.O. twice, T.O. then Henry, Henry then T.O., or Henry then Henry. Now, what does, let's see. What does probability of 0 mean? Okay, probability of 0 is going to mean no TO buttons. How many options for no TO buttons? One out of how many? 1 out of 4. Okay. What's probability of 1 mean? You get 1 TO button, yes? How many options are there to get 1 TO button? It's 2, aren't there? Okay. Or I think I had originally written in my notes as you could think of it as 1/4 plus a 4th. But either way, it's 2/4, or in other words, 1/2. What would be the probability of 2? And then you're back to 1/4, aren't you? So 1/4, 1/2, and 1/4 for my probability distribution. Excuse me. Now, before I move on, okay, when they're asking you for a probability distribution, they're asking you for the various probabilities. Notice I have a definition at the bottom that says what a uniform probability distribution is. And a uniform probability distribution assigns the same probability to each outcome. What do you notice about the one we just did? Is this a uniform probability distribution? No, because I got 1/4, 1/2, and 1/4. So this one is what we would call not uniform. Okay, it's not uniform because those are not equal. What if I go back up here to part A?
Yes.
When we were just picking one button, this one was uniform. So when you're asked whether or not a probability distribution is uniform, if they're all the same, it's uniform. If there's different answers, then it's not uniform. Okay? And I don't know if you notice here or not, we'll talk about this later, but I'm going to go ahead and give you a heads up. What do my probabilities all add up to be?
100%.
100%, 1. Okay, 1/2 and 1/2 is 1. 1/4, 1/2, and 1/4 is 1. Or in other words, yes, you can think 100%. Okay. We're going to talk on this next page about a couple of examples and whether they are or are not uniform probability distribution. So we're going to write out the probability distribution and then decide whether or not they are uniform. This one, I'm not sure, the copy machine did not do this picture justice, did it? Sorry. On my copy, maybe it's also just my eyes not being able to see the small stuff. I think the G's and R's are hard to figure out the difference of. But, okay, you select 2 marbles at random from the bowl. For each situation, define the theoretical probability distribution for selecting a number of what?
1.
Red marbles? Okay, so this, in other words, our success is it a red marble? On the sample space, 0, 1, 2. And then we'll answer, is it a uniform probability distribution? So, 0, 1, 2 is going to mean what? 0 red marbles, 1 red marble, and 2 red marbles, yes?
Yeah.
Okay, so in example A, you select 1 marble, you put it back in the bowl, then you select a second marble. And so let's start with probability So what's probability 0 going to be? 0, which means that you get what? No red marbles, which would equivalent to both being green in this case. Yes? So I'm going to have us actually find the possible different options here, because I need you guys to see something. So probability of green and green, which, yes, here in a moment, is going to be probability of 0 red marbles. Probability of green and green. Okay, think about what we've done in the last couple of lessons, what you did on the quiz. What's the probability that your first marble is green? 3 green out of 5 marbles. So 3/5. And, so now it's a second draw. Remember, that's a multiplication thing. First of all, I used the word and, but it's 2 different draws. And what's the probability my second marble is green?
Wait.
What did I do? I put it back in the bowl. So what's the probability my next marble is green? 3/5. Now, I'm going to end up going 3/5 and 3/5 was easiest for me to find the probabilities, but I'm going to end up going decimals here in the end, which it's 9/25. I'm trying to remember what it is as a decimal. I just looked and I already forgot. As a decimal, this is 0.36. Let your calculator do the talking there, yes? Okay. Now, let's go with the probability of...
So the probability of green and green is 0, right?
Yes, and I'm going to pair that up here in a moment.
Okay.
I'll pair that up here in a moment. I'm going to kind of going with the idea of let's get the basic information, and I'll pair up what does 0, 1, and 2 mean. So probability of green and then red. So probability of green on the first draw is
3/5.
3/5. 3 green out of 5 marbles. What's probability of red on the second draw?
2/5.
2/5, because we're putting the marble back right now, aren't we? What is 3/5 times 2/5? 6/25, which is 0.24. Now, we're going to talk red and green. So we're going to switch the order. Is it going to matter in this case? In this case, it's not going to matter, is it? But I'm having you consider this because sometimes it will, and we'll get to that. So, probability of red on the first draw, well, there's only how many red? 2 out of 5. But then you put that marble back, probability of green, 3 out of 5. So yes, I know some of you gave me crazy looks, that's okay. It is the same. Okay? And what's the final possibility? You could have gotten 2 green, you could have gotten a green then a red then a green, or you could get red both times, yes? So what's the probability of the first red? 2 red out of 5? What's probability of the second red? Still 2 out of 5 because we're putting them back. So that is 4/25, which is 0.16. Okay. Now, yes, you can streamline that on your own if you want. But here's the deal. There's a reason I had us write these out. Okay. Using the information we just found. Probability of 0. Probability of 0 would be 0 red. What's our probability of 0 red? What is that? That is the 0.36 because 0 red would be 2 green. Okay. What's the probability of 1 red? 0.48. Because why? It was 0.24 chance that I get just a red on the second draw. 0.24 chance that I get just a red on the first draw. So we have to add those two probabilities together. 0.24 plus 0.24, which is 0.48. That right there is the reason I took us the long way, guys. And what's the probability of 2 red?
0.16.
0.16. Now, here's a little check for you. Does my probability distribution add up to be 1?
Yeah.
If you add 36, 48, and 16, that adds up to be 1. So that's the little hint. I have it written down here, but it's always a good check that you've gotten everything accounted for if your sum is 1, or in other words, 100%. Now, the question was, is this a uniform probability distribution? No, because the chances of getting a no reds versus 1 red versus 2 red are not the same. So this is not uniform. Okay. Shall we try B? B's going to be a little bit different, isn't it? What's different about B? You select one marble and do not put it back in the bowl. Then you select a second marble. So let's redo our probabilities here. Okay, probability of green and then green. So what's probability of green on the first draw? Still 3 out of 5. What's probability of green on the second draw? 2/4. Because I drew a marble, I didn't put it back. Well, so now I have only 4 marbles to draw from. And because it's the same color, we're going to assume I got the color of interest the first time. So this is 2/4. So 3/5 times 2/4, which is 6/20, which reduces to 3/10, which is the decimal 0.3. Okay, same order as last time. Green and then red. So probability of green on the first draw. Still back at the original, 3 out of 5, yes?
Yeah.
What are we going to assume? I drew a green and I'm still holding it in my hand. What's the probability of red?
2 out
Yep.
of 4.
There's 2 reds out of only 4 marbles. So 2/4, or I heard 1/2 out there. You're more than welcome to write 1/2 down. I'm just not, that way in case someone looks back and says, wait, what? So this one is also 6/20, which is 3/10, which is 0.3. Reverse it.
Couldn't you just do like that one and then multiply that?
Let's reverse it and try it. So what's the probability of getting red on the first draw?
2 out of 5.
I draw a red. We're going to assume I'm still holding a red. What's the probability of a green?
3 out of 4.
3 out of 4. Now, here's the question. I mean, the probabilities themselves are different. What does end up happening this time? It still multiplies to be 6/20, 3/10. However, because it is dependent and we're keeping that marble, I'm going to definitely encourage you to not just multiply by 2. Now, up on the top one, could you just multiply by 2? That would be a safer bet. On the bottom one, I'd be more careful there. This time it was the same. I'm not 100% sure. I can always guarantee that. Maybe, maybe not. I don't know. Okay. And have you guys done red and red yet? What's the probability of the first red? 2 out of 5 marbles. I drew a red. I'm holding a red. What's the probability of the second red? 1 out of 4. 1 less red marble, 1 less marble. Multiplying, we are at 2/20, which is 1/10 or 0.1. Okay. We were asked for the probability distribution of 0, 1, 2. So I need the probability of 0, the probability of 1, and the probability of 2. Okay, what's my chance of 0 red marbles? 0.3. What's the chance of 1 red marble? 0.6, because there is the 0.3 plus the 0.3. And what's the chance of 2 red marbles? 0.1. Huh? Okay. Is this uniform? Caitlin? Thank you. Is this uniform? This one is also not uniform.
That's all.
Okay. Did my probabilities add up to 1 appropriately? Did you check? Again, I found that a helpful check just to make sure, okay, I didn't goof anything up along the way, did I? I didn't misreduce a fraction or misadd or mismultiply, something like that. Okay. So, when you're asked for probability distribution, you're finding the probabilities of each section. Be aware you sometimes will have to add up pieces to get one of these. Okay? Because we are assuming that, we have to think about the order there. Okay. This was all based on theoretical probability. The idea of, we see the 5 balls in the bowl, 3 are green, 2 are red. What is the probability just based on what we're picking? In this next section here, we're going to be looking at experimental probability distribution. When we talk experimental as opposed to theoretical, it's based on numbers provided. So more like survey numbers. I don't really want to say experiment because it doesn't really sound right, but your experimental is based more on numbers surveyed or whatever. So in this situation, a cell phone company surveyed 500 households about the number of smartphones they have that are in use. Would you recommend that the company concentrate on selling data plans for individuals or plans for families with 3 or more smartphones? Okay. And what we're going to look at here is finding the experimental probability distribution by finding each relative frequency. Okay, so we're still finding probability distribution. The only reason we're saying experimental is because we're not basing it on what we know about rolling a die or picking a marble from a bowl. We're basing it on data provided. Okay, so first of all, to find this, it asks us to find the relative frequency. And I'm basically going to add a line in my chart here, okay, to find the relative frequency. So think about the data provided. What is the probability, based on the data provided, of there being 0 smartphones in a household? It happened 10 times in their survey. Out of a lot, what is that a lot number that was provided? 500. So how are we going to find this relative frequency? We're going to do 10 out of 500. What is 10 out of 500?
1 out of 5.
Okay.
50.
1 out of 50.
Yeah.
0.02 is a decimal, which typically they're going percents here. So this is what is a percent? 2%. Okay. Continue. What is they call it relative frequency. I'm using that vocabulary because I don't want you to be thrown off by seeing it in the homework. Basically, we're finding the probability, aren't we, of one smartphone per household. Well, what am I doing here? 66 out of 500. Do the math. What's my calculator say? .132. And I will say for the most part, the homework and the notes are asking for whole percents. So 0.132 is approximately what whole percent? 13%. Okay, continue. 2 smartphones is 120 happened 120 times. So 120 out of 500 is 0.24, or in other words, 24%. 3 smartphones. 144 out of 500. 0.288, which is 29%. 79 out of 500. 0.158, or which rounds to be approximately 16%. 37 out of 500. 0.074. My brain says 7.4%, but if we're going to whole percent, that's 7%. And the last one, 6 or more, happened 44 times out of 500, 0.088, so 8.8%, or approximately 9%. Okay, so now, in order to look at this, they want us to graph it. And so we will start there tomorrow, and we will graph down here smartphones per household, basically making a bar graph. You can fill in the bar graph starting tomorrow, just like that. And then we'll talk about whether they should focus on individual or family plans.